This program is a presentation of UCTV for educational and non-commercial use only.
Good evening and welcome. My name is Nigella Hilgarth and I'm the Executive Director here at the Birch Aquarium at Scripps Institution of Oceanography. And it's a great pleasure to see you all here tonight. It's exciting to have such a great crowd for a wonderful topic this evening. And I'm going to now introduce our speakers. It's a great pleasure to introduce Miriam Goldstein, Pete Davison, and Chelsea Rochman. And they're going to talk tonight about a cruise that they did recently that they organized and led called SEAPLEX. But to me, it's so much more than that. It's not only talking about a very important and relevant topic, talking about pollutions, trash, plastic in our oceans. To me, it's also the story about a very engaged and energetic group of students of enormous perseverance until they really were able to carry out the work that they wanted to do. Very enterprising doctoral students, they identified this project and then they sought the necessary resources to do it. And in this case, that means ship time. That means actually trying to get one of the mighty vessels that Scripps Institution of Oceanography runs and take that time to go out and look at the great garbage patch. And as you can imagine, that's actually quite a difficult thing to organize. Miriam Goldstein, who I believe is going to speak first, actually was the chief scientist on this cruise, and then Pete and Chelsea were co-chief scientists. And they're all graduate students that are approaching the issue of plastics in the ocean from varying perspectives. Miriam is now a fourth-year PhD student here at Scripps, studying biological oceanography. And for her thesis work, she's investigating the distribution and abundance of plastic debris in the North Pacific Gyre, as well as the potential for plastic debris to impact with the distributions of the various invasive species. And as I mentioned, she's the principal investigator or chief scientist on this cruise. Now, Pete is now, I believe, a sixth-year student at Scripps, PhD student in physical or biological oceanography. And he focuses on a really neat group of fishes that vertically migrate called mytophytes. And he's been working on a number of cruises, and during the SEAPLEX he was investigating the plastics in the guts of these fishes. Chelsea is a PhD student in a joint program between UCSD State University and UC Davis. And she's working to better understand the chemical aspects of the plastic debris in the marine environment. She's particularly interested in those specific organic pollutants that are in the ocean and how they might adhere to the plastic, be absorbed by the plastic, and therefore might actually get into any organism that eats the plastic debris. She also has worked here at the Birch Aquarium and is very much part of our team here. We'd appreciate it if you could keep all your questions until the end of the talks, and then I know that all three speakers will be very pleased to answer your questions. So without further ado, please join me in welcoming our speakers tonight for Let's Talk Trash.
Oh, thank you so much for that fantastic introduction. So I'm going to introduce the SEAPLEX Expedition and talk a little bit about why we went to the middle of the Pacific to look for trash and what we found there. And then Pete and Chelsea will talk a little bit more about their research, so you'll get to hear sort of the broad view and the narrow view. Okay, so about 3 years ago, we started seeing all these headlines, and we became very curious about this Great Pacific Garbage Patch. There was an enormous ocean dump. It was twice the size of America. It was 3.5 million pounds. It was between Hawaii and Japan, and we wanted to know more about it. And we invited a speaker down from the Ecology Marine Research Foundation, which is the organization that has done a lot of work out there. Dr. Marcus Erickson was the person who came down and heard his talk, and were really inspired to continue Scripps' tradition of North Pacific exploration, although on a more depressing topic than most. So a group of 7 Scripps graduate students, organized by myself, wrote a proposal to the UC Ship Funds, which is a really fantastic program we have at Scripps that allows graduate students to apply for their own cruises. And it's a competitive process. We were granted the funding, and all of a sudden we were going to the North Pacific Gyre. So I'm going to just quickly talk about why we went all the way out there. This is a diagram of the major ocean currents. So here we are, and you see there's 5 big circular features, and those are the subtropical gyres. And they're driven by the major winds of the world. So the westerlies that go like this, and the trade winds that go like that. And then as the Earth turns, the water moves to the right and starts moving in a clockwise motion. So this is the North Pacific that I'm focusing on, but all the gyres do more or less this. And so it basically acts like a big, slow whirlpool. The technical term is convergence zone. And it brings things towards the middle. So here we are. If we throw a bottle off California, it's going to go approximately this way. And throw a bottle off Japan, it's going to go approximately this way. And if it doesn't sink and it doesn't go anywhere, it's sort of stuck there forever. And so that is why it's thought that trash is accumulating in this part of the ocean, and perhaps also in these other gyres. Here's a closer look at the North Pacific. These colors actually are the winds. So the red is lots of wind, white and blue is not so much wind. And so there's lots of wind coming down in California, lots of wind going with the trade winds around Hawaii. But here, you see this big calm spot where I put the really intimidating big black star. And so that is where we decided to go based on research, based on the oceanographic conditions, and based on research, most particularly by Algalita. And so I also wanted to point out, so you can see the water coming around this way, or rather the winds, and Hawaii is right there in the middle of the higher winds, so it ends up acting like a big comb, which leads into my next slide. These are my sad pictures. These are all pictures from Hawaii. So the islands act like a big comb, and things wash up on places that are otherwise pretty uninhabited. So there's an albatross with some fishing line stuck on its beak. This is an endangered Hawaiian monk seal with some rope stuck on it, and a baby albatross on the beach with there's some fishing debris and some bottles and some seawater filters. And so these are just some of the impacts that we can see with the larger pieces of debris. Oh, I wanted to mention that also a line these days is made out of plastic, most lime made out of polypropylene, so it doesn't break down either. The SEAPLEX Expedition got 20 days on the New Horizon. It was funded, as I said, by the UC Ship Funds, and then later became a collaboration with a nonprofit called Project Kaisei. And we all went out from San Diego, went pretty much due west, noodled around in here in the area of the big black star I showed you earlier, and then continued into Newport, Oregon. And there's Hawaii for a little frame of reference. So we were on the RV New Horizon, which is one of the Scripps research fleet. It's the medium-sized ship. It's 175 feet long. There has 17 science crew and 12 ship's crew. And is really just a fantastic research platform. We were so thrilled to be able to go out there. So I'm going to show you a little video of what we did on the ship and just talk over it so you can get an idea of what it looks like and the kind of nets and the kind of procedures that we did, if my video goes, which it is. Excellent. This is taken largely by our absolutely fantastic communications person who lurks somewhere in here, Mario Aguilera, who we're very fortunate came out with us. So I'm going to show you a bunch of different kinds of nets in action. You can't necessarily see all the debris, so most of it, as I'll show you later, is in these little particles. So we use techniques usually used on zooplankton, on the microscopic animals, to look at the debris. That's the biggest piece of equipment we were using. Pete will talk about it later. It's the midwater trawl used for catching deeper fish. And so it can be sort of interesting deploying these for especially someone like myself who didn't have a lot of sea experience before all of a sudden there we were in the middle of the North Pacific. So it was something of a learning curve, but I think that is the clever purpose of the people who designed the UC Ship Funds, is you learn a lot very, very quickly. We also were able to use a small boat, a small inflatable boat, to go look for pieces of debris away from the ship because we were more maneuverable. This is a ghost net that we found, and the video will now go to some of those broken down but still visible pieces that we collected using the small boat. So most of the pieces we could sight visually were still not very big, with the exception of the ghost net. A lot of like broken down crates and bottles and things like that, unrecognizable hand-sized pieces of plastic. So hopefully, I think it now goes to random research techniques for that scientific flair. And so, but you can. So you can get an idea of just basically what it looked like, which I spent the entire time standing at that sink, for the most part. So, and there is the science crew again. Okay. All right, so what we saw. So these are photos of things we pulled up in the backs of our nets. So this is concentrated density. These are all things that were gathered up by the nets. But you can see that the pieces of plastic are really small. There's a ruler in centimeters for scale, and a little squid, flying fish, and a lanternfish, which you will hear a lot more about with Pete. And there are these little pieces of plastic that are a couple millimeters or centimeter large. And so a millimeter is about the thickness of your fingernail. So they're very small, and some of them almost microscopic. On this picture on the right, these are by-the-wind sailor jellyfish, or Valella. And here, they're also with these pieces of plastic. So the important thing about this is that these pieces are the same size as the animals that we're seeing in the nets. So these animals, they're the right size to really be interacting with the animals, either being ingested or being lived on or something like that. But we didn't see huge conglomerations or huge floating trash heaps or anything that looked like a dump. What we saw, the highest density of plastic that we saw the whole trip, or at least that I saw, was right here. This is the most I saw in one place without having to deploy a net. So there are all these little white dots are plastic, and there's a Dipnet, which is about the size of my arms around for scale. So that was only on a very calm day, but I really was surprised because there we were really in the middle of nowhere. I don't think we can get more in the middle of nowhere than 1,000 miles from California and 1,000 miles from Hawaii, outside of the shipping lane. So we were really far away, and just seeing all those little pieces just floating on the surface really far away, I found quite sad. There's our ghost net again. This is probably the largest piece of debris we found. And it was, I don't know, it was longer than the small inflatable. And for those of you who might not have encountered them before, ghost nets they're discarded fishing debris. They're lost by mistake, they get tangled or they get cut loose, and they get snarled into this big hairball of net. But the disturbing thing about them is they keep on fishing. They're still a net, they're still made out of plastic, they never go away, so they can keep on catching things and entangling things pretty much for a very long time. So turtles and birds and whales often tend to get stuck in these ghost nets or in discarded fishing debris. And this is the strangest thing we found. Actually, we are very fortunate tonight. This is Lucky the dog. He's making his very first public guest appearance. And here, I'll put him right up here. He can watch you back. So we found Lucky stuck in a ghost net, and there he was, just floating there just like that. And it was very disturbing. We don't know where he came from. He was not very overgrown with sea life. Let's say he was rehabilitatable with lots of dish soap and elbow grease. Darcy, one of the graduate student researchers on board, spent a long time scrubbing Lucky. But he has been rehabilitated by the aquarium, and here he is. And I also wanted to show you our other happy, non-trash related, most spectacular find. It was something that made the science crew all really excited, and so it's in video form. Our collaborators did a lot of videos, which was fantastic.
On day 3 of the SEAPLEX voyage out to the North Pacific Gyre, aboard the New Horizon, a Scripps oceanography vessel, together with Project Kaisei, you're not going to believe what happened when a group of scientists found a dead squid. Watch this.
Hey, there's another net over there in the same spot. Grab the other net.
So this is what scientists get to do. They get to play with dead animals.
Yeah, I've got a tape measure. Yeah, go get it. The lens might be gone. No, but I don't feel it. That is Chelsea going for the squid's eyeball. You'll meet her later. I'll back out. There you go. Oh yeah, there you go. Yeah. The lens fell off. That is my voice egging her on. And there's the beak down there, which looks like the parrot's beak. That's what the squid eats with. Oh, I don't know, but I passed. This is the squid's pen, which is it's a modified shell, like a very highly modified shell. This one is madness. I've never seen anything like it. Whoa, nice eyes. Yeah. So that was our exciting, large, very, very, very dead squid. Extremely dead. Really quite dead. And had the smell to match. The captain was less excited, but we cleaned off the deck very nicely after we took it. All right, so I also wanted to do a quick look into misconceptions about the gyre, since there is so much interest in this issue, and there are sometimes some things get perpetuated on the internet that are less than correct. So we didn't see a big swirl by satellite. That's because you can't see the plastic by satellite. Sorry, that's my big swirl. You will see this picture if you Google pictures of the North Pacific Gyre. It's still up on Tree Hugger, despite my best attempts. But this is neither the gyre nor plastic. This is actually Japan, and this is a plankton bloom of coccolithophores, probably. So you cannot see plastic from satellite currently. At least we don't have a good way to do it yet. So there are no satellite pictures of the extent of the trash because it's too small to see visually, and it doesn't reflect in a way that you could see it with other wavelengths. It also does not look like this. You will also see these pictures if you Google North Pacific Gyre, but this is Baltimore, I think. I'm sorry to anyone from Baltimore, that's what it said. And I think this is somewhere in an urban area in the South Pacific. It was not labeled, but it was labeled gyre, but it's not. For that, you cannot get a lovely little canoe 1,000 miles away from any land. So it did not look like that. The ocean just looks like ocean, but the pieces are very, very small. I forgot to mention, so we saw those little pieces of the size that we're passing around and smaller for 1,700 straight miles. So we did 132 surface tows, which was where we found most of the plastic. And for the central 100 of those, the ones farthest away from land, we got plastic in every single tow. So, but the vast majority is those little pieces, and you can't really see them visually. They're just very small, but very, very, very abundant. I wanted to mention our outreach effort because we put a lot of work into it because we think this issue is so important. I'm not going to go through it, but if you want to find out more about us, you can go to our webpage or our blog, or you can just Google SEAPLEX. We're very easy to find. We got a lot of media attention when we came back. We were a little shocked, but one of the things that we are trying to do is is communicate what it's like out there. So it's one of the reasons I'm so happy to be here today. So definitely we found it across 17 miles, but it's definitely not a dump or an eighth continent. It's actually, we think, maybe a little scarier than that because the pieces are so ubiquitous and so small. So what we're doing now is we're working on our samples and our data. We took as many of jars of stuff as possible when we were out there because ship time is very precious and we were out there for, you know, not infinitely long. So what you do is you put a lot of stuff in jars and you deal with it back in the lab. There's a cameo of Pete in his natural element. And so we're working on, the priority is how much plastic did we see and where was it? We're still working on that data in the lab, counting out all those little pieces and measuring them. So working on getting that out as fast as we can, but it is a lot of labor. We would love to go back. We're working on applying for grants to go back and follow up on some of the things that we are now curious about. For example, we still don't have a good idea of how deep it goes, and we don't know if it goes all the way to the bottom. So it's some of the things that we'd like to look at. And be happy to talk more about that later, but I'm running out of time. My own research is, I wanted to mention really quickly, because it is what I'm here for, is I work on fouling communities. So I'm looking at what it means to have all these hard surfaces in a world that should not have very many hard surfaces out in the middle of the ocean. This is our bird researcher, Andrew. I love that picture of him hefting this buoy, and that's all gooseneck barnacles on the bottom. Here's some anemones that are very far from home on this piece of crate, and that's a bryozoan on a very tiny piece of plastic. I'm sorry, a very tiny piece of something. Anyway. And so thank you so much. And I will pass the floor to Pete. Oh, we actually did see this double rainbow. It was spectacular. Spectacular stars, spectacular rainbows. Even on the depressing nature of this mission, it was really amazing to be out in the middle of the ocean. Some lucky science crew members, who are not me, saw even a meteor shower way out at sea and said it was amazing. So thank you so much, and I'll be back to answer questions at the end.
My name is Pete Davison. I'm a graduate student at Scripps Institution of Oceanography. And my part on the SEAPLEX cruise was to look at plastic ingestion by fishes, and Chelsea may talk a little bit more about why that's important. This is our ship, the New Horizon. And why is the topic of fish eating plastic important? And fish live and feed where plastic pollution is abundant. Some literature reports suggest that fish may eat plastic. It's potentially harmful to the fish, and pollutants may enter the food chain. So it's not good to eat plastic. Toxins stick to the plastic. Chelsea will tell you more about that. And we don't eat these little fish. These are lanternfish or myctophids, but other fish that we do eat them. So for example, tuna may eat some of these fish, and we in turn eat the tuna. And plastic entering the food chain could be of concern to people. And we wanted to demonstrate that this pathway is possible. So I'm going to talk a little bit about ocean ecology. And in the ocean, habitat structure is vertical, mostly temperature and light. But if you want to see an ocean temperature change of a few degrees Celsius, you have to go hundreds of miles horizontally, but you only have to go a few meters vertically. And all of the food in the ocean is near the surface, or comes from the surface. All the phytoplankton, the plants in the ocean, are in the part of the water column that's illuminated by light. So this is coincidentally where the plastic is. The plastic floats for the most part. And so if we're going to look for fish eating plastic, we want to look for fish that live in the surface water. In the open ocean, many of the fish are not in the upper water column during the day. They migrate, and they migrate down in the daytime and up at night to get away from big predatory fish like a tuna, which feed visually. So during the daytime, the fish that I'm investigating are hiding, if you will, in the dark, so they don't get eaten by tuna. But at nighttime, they come up to the surface and they eat zooplankton, small crustaceans, which are in turn eating the phytoplankton. And you can see my art skills there on the phytoplankton. But the phytoplankton is the plant of the ocean. They're eaten by very small crustaceans, which are in turn eaten by small fish, which get eaten by bigger fish, and so forth. So here's some more pictures of our study animals. These particular fish are mesopelagic fishes. They're zooplanktivores. They eat zooplankton, those crustaceans I mentioned before. Many of them have photophores. And these photophores are small light organs. They're the little circles on the bellies. And those organs are there to countershade, which means that if you're underneath the fish and you're looking up, you might see a silhouette, and this is their defense against that. They kind of light up on their belly, and it's hard to see them from below. But it's very common. The fish at the bottom left there is a hatchet fish. They're very cool. And to the right is a bristlemouth or a cyclothone, and we have two myctophids on the right and a deep sea smelt on the top. And all of these fish are about the size of your finger, roughly. And there's about one of them per square meter of ocean surface in the open ocean. So over the whole surface area of the ocean, there's approximately 1 billion tons of these fish. So they're ecologically important simply because there's so many of them and they live everywhere. So our sampling methods were diverse. I begged fish from everybody who put a net in the water. So this is a Dipnet. It's like a giant butterfly net. This is the Manta net. Miriam showed you a video of this. I took the fish out of there. The bongo net is made for zooplankton. It does capture fish as well. And this is my net, the big one. This is a midwater trawl called the Ozeki trawl, and it's launched off an A-frame. It's a big production. It takes 5 or 6 people, and it catches lots of fish, which is what we were going for. This is what it looks like in the water. And when it comes up, the whole catch is at the back of the net. So if I go back to this, the right side of this net is like a funnel, and it ends in a plastic can called the cod end, and that's where the catch ends up. So once we get all these fish on board, we do what's called a rough sort. We put them in the sorting pans, and we pick the fish out and put them in jars, and I've got the jars on ice here so the fish don't go bad. And then the zooplankton go in another jar. So we didn't do much more than that at sea, identification-wise, because you don't have much time. And then these samples were preserved in formaldehyde so that we could look at them later in the lab. Since we're looking for plastic ingestion, the obvious thing to do is to cut them open and take the stomachs out and look for plastic. And this is Rebecca Ash, a student who isn't here tonight. I don't think Rebecca's here, but she's my collaborator on the fish, another student at Scripps. And the picture on the right shows an actual fish with an actual fish stomach dissected out. And this is that same stomach under the microscope. And it's hard to see, but the white gooey stuff there is partially digested crustaceans. I don't know if this fish had plastic in it. The odds are against it, but we did this one a few days ago. We take these stomach contents and we stain them with a stain that stains biological material, but which doesn't include plastic. And then we've filtered the liquid with the stomach contents onto these little white filters. And this one, number 554, has a blue piece of plastic, which didn't come out well, but there's a better view of it, the same piece. So we did find that some of these fish are indeed eating plastic. So this is direct evidence of this. The evidence prior to this has been indirect or unpublished. So we now know that they do eat plastic, and that contaminants or pollutants on the plastic could, well, it actually is entering the food chain. And I think this is the first published, or it's not published yet, but when I do publish, it will be the first published evidence that these fish are eating plastic. And I'm done. Chelsea?
I'm going to go ahead and start. My name is Chelsea Rochman. As Nigella said, I'm a graduate student of UC Davis and San Diego State, so I don't go to Scripps, but I did work here at Birch Aquarium for 4 years. So I should be really comfortable talking out here, but I'm not going to lie, I'm a little nervous. There's a lot of people here. But I'm going to talk about what some people call the other plastic problems. So you hear a lot about mechanical adverse effects like entanglement. I'm going to talk about chemistry, which might sound daunting to a little of you, so I'm going to keep it fairly simple, but it's a really important topic. So I will go into the other plastic problem. And for my talk, I'm going to go into a lot of background on this issue and just explain what this is all about and what is the toxicity associated with plastic in the ocean. Then I'll talk a little bit about my own role on the cruise and a little bit about my own research. So I wanted to start out with this quote because I think it's kind of ironic, yet at the same time it has a lot of truth to it. So plastic is not evil, right? We've had a lot of great gains from plastic. It's done wonders for the medical industry. It's very convenient, as we all know. And so before plastic really picked up speed around World War II, this quote was, "How much brighter and cleaner a world than that which preceded the plastic age." So plastic production has greatly increased because it was a great product. And it's increased from about 0.5 million tons in 1950, this is yearly, to 260 million tons today. So we are producing a lot of plastic. Now, some of the reasons why it's so great is it's lightweight, it's cheap, and it's persistent. You can use a Tupperware for years upon years, but if it ends out in the ocean, this persistence can be a problem. So plastic, as we know, doesn't biodegrade, it photodegrades. So as it's out there in the sunlight, it's going to break down into smaller and smaller bits, which is what Miriam showed you, right? So that's why we're seeing a lot of these small plastic pieces. So just to kind of go over quickly, what are these mechanical adverse effects that you hear about all the time? So entanglement, you see a lot of images of sea lions wrapped in nets, and it restricts their growth, it restricts their breathing. Sometimes organisms ingest plastic, as Pete talked about, and there are mechanical effects, right? It gets into your GI tract or your stomach. You can't digest it, it gets stuck there, you don't feel hungry, and therefore you don't get nutrients, and organisms can starve to death. So we know that over 100 seabirds ingest plastic, plus other animals, and 250 marine species are known to be infected by entanglement. We see images like this all the time. That is a plastic bag, which looks a lot like a jellyfish, which sea turtles love. And when they eat it, they feel full. But of course, they're not. They don't have nutrients, and they starve. And there's lots of aquariums that have restoration projects trying to take in these turtles and fix them up. Now, we didn't see plastic bags out there. We didn't see a lot of these big pieces. So I'm going to talk about these smaller pieces. So if these small pieces are getting in an organism, well, probably not going to feel full. They might be able to send it through their body. But what about the chemistry? So these chemical aspects are beginning to gain a lot of attention, and I think it's deserved. It's a good thing to learn about, and scientists are kind of struggling to try and figure out what is going on, because right now this topic is a little bit less understood. So basically there's two sides to this story. So some of this stuff you guys are going to be pretty familiar with. Additives, monomers, and oligomers, you can ignore those words. It just means those things are in plastic through manufacturing. So they're in there when it comes out of the store. And sometimes they leach off of the plastic. So I'm sure a lot of you have heard of the No. 7 Nalgene bottles that they were telling you not to buy, or baby bottles, because they leach BPAs, and BPAs can be toxic to children at certain concentrations, or even adults. Phthalates is something in almost all plastics, and at really high concentrations it can cause an issue. Styrenes, of course, come from styrofoam, and then nonylphenols are another toxin that does leach out of the plastics. Then you have these things which we like to call POPs. There's a million acronyms in the chemistry world, so I'll try to avoid them. But basically, POPs just means persistent organic pollutant. They're persistent because they hang out in the environment for a long time. They're organic and they're pollutants. So basically, you're probably, and that looks lovely there with the E on the other side, but whatever. You're probably really familiar with DDT from Rachel Carson and the eggshells of the bird. So basically, DDT, when it gets in an organism, it causes eggshell thinning. When they go to sit on their eggs, they can break, and basically they have a hard time with reproducing. So DDT is illegal in our country, but it is still used worldwide, and it's very persistent, so we still find it in our environment, even in the San Diego Bay. PCBs are a combustion product. PAHs come off of your cigarettes or out of your car exhaust, or if there's an oil spill, you get a lot of these in the ocean. And PBDEs, or polybrominated diphenyl ethers, are like, if you're in the chemistry world, this is what's popular right now. These are flame retardants. Basically, if you own a piece of furniture that's over 10 years old, you have a lot of your weight of your couch is made of these PBDEs, because we don't want to sell things that are going to be flammable and blow up in your living room. So we've loaded our furniture with this stuff, but now we're finding, well, this might have some consequence. So what does this have to do with plastic, right? Well, basically, it adsorbs onto plastic. This word looks like a big fat typo, absorption, but it's adsorption. Instead of like going in like a sponge, it sticks to the surface. So it's like a magnet for these pollutants. And we find these pollutants at concentrations over 1 million times that in the water column on the piece of plastic. So they're basically like magnets for these toxins in the water. So what does this mean? Who cares? There's a lot of chemicals involved in our plastics. Well, we know that ingestion of plastic is more frequent than entanglement. We saw a lot more small pieces than we did big, and those are pretty easy to eat for a smaller organism. We know that over 180 species are documented to ingest plastic: birds, turtles, fish, marine mammals. And it's not just organisms in the ocean, right? There's terrestrial or land species as well. And ingestion of plastic is a suggested exposure route. So let's say I eat a piece of plastic, not that I will, but if I did, and those toxins on the plastic are going to be more attracted to my fat than they are to that plastic, because that's just the chemistry side of those toxins. So when I eat it, it's going to go into my tissue, and because they're so persistent, they're just going to stay in my fat, or I'm going to do they might somehow come out, I metabolize them, and they become toxic, but they're going to be in my body. So we're wondering, if these organisms are eating plastic, are they getting into the food chain? And there is some evidence of this. People have done lab experiments feeding plastics to organisms and found that leaching does indeed exist. So what? Again, who cares, right? They're just chemicals. Well, we know that BPAs at certain concentrations, so it's the dose makes the poison, right? If I eat a little bit of BPAs, I might be okay. But if I have enough, it's an endocrine disruptor, which basically means it's going to act like an estrogen, and it's going to make me have problems with reproduction. This is when we find feminine effects in male, like frogs with eggs in their testes, or fish with eggs in their testes. So reproductive issues. DDTs are neurotoxins. If I were to feed a fish DDT, they're going to start to convulse. It's going to cause a lot of problems for them, and then other neurotoxic effects. PCBs are carcinogenic. We all are familiar with that word. They can cause cancer. PAHs also can cause cancer. Phthalates are endocrine disruptors. PBDEs, which are those flame retardants, are carcinogenic, and they can interact with our thyroids, which are also really important for our hormones. So this is indeed actually an issue. So I'm going to talk a little bit about how we get these high concentrations, because if I eat a small piece of plastic, I'm not going to get a high enough concentration in my body to have an effect. But let's say there's all these tiny pieces of plastic out there in the ocean, like there is, like we saw. And we have 10 krill. And each krill eats one piece of plastic. So they each have one amount, let's say, keep it simple, of toxins in their body. Then we have 2 mackerel come along, and I think Pete was a little concerned that mackerel might not actually eat krill, but maybe they do. But let's say that each mackerel eats 5 krill, and now they have 5 times the concentration of that pollutant in their body. And then let's say a tuna comes along and eats the 2 mackerel. And now they have 10 times the concentration in their body. Now let's say I'm hungry, and I go to the store and I buy that tuna and I eat it. I also have that magnified concentration, and this is termed biomagnification. So it's magnifying up the food chain. So basically my role on the cruise was to kind of look into some of these effects. What's leaching? What's adsorbing onto the plastic? Are they going into the organisms? And basically what's going on out there in the Pacific Gyre. So I wanted to look for the presence of these plasticizers, so the stuff that leaches, the phthalates and the BPAs, in environmental samples, water samples. And biological samples, I use salps, which are like a pelagic tunicate. Fish, I have some of that dead squid, which I'm not sure how helpful that will be. And then also look at the adsorption, or that magnet effect of all of those organic pollutants sticking to the plastic. So what's out there in the gyre, what's sticking to them that far from land. So I have some samples, and I want to see if I can, first of all, see these chemicals in the environment, and second of all, if there's enough to quantify them. And in water samples, salps, and fish tissue. And then I also have some plastic samples from the gyre where I can try and quantify and look for the presence of these different organic pollutants. So this is what I'm working on right now. I don't have any data to show you because unfortunately chemistry is really expensive, but I'm ordering the chemicals tomorrow and I'm really excited. So I'm going to actually get to start in the lab analyzing my samples, and then I'll have data. So instead I'm going to talk a little bit about my goals in all of this. So basically, as a scientist, I want to be able to better understand the plastics as a medium for toxins to enter the food chain. And then maybe eventually how this might relate to human health, if this is affecting us. Are we eating these species? Maybe not in the middle of the gyre, we're not eating that many species, but this happens in coastal areas too. So plastic is found in many places in the ocean. And then I hope to be able to continue to educate policy and the public, because I think doing things like this and educating the public is one of the best things you can do, because the solution starts with us. I would say that plastic is kind of a unique environmental issue in that for some environmental issues like climate change, it's a really serious problem, but you can't go outside and necessarily see it and touch it. You can't walk outside without seeing litter on the beach, on the side of the freeway, in a park. This picture is in San Diego. Has anyone been to the Tijuana River Valley where you go and you see this plastic and the trash coming in? So, you know, it's close to us. And so I think out there in the middle of the ocean, it shows us, look what we can do. Now how are we going to make a difference? And I think education is really important. And then hopefully I can use what I've learned in my own life to help make a difference. And it all starts here. So hopefully you guys learned something tonight and you can take something away from it. We want to thank a lot of people. And if I read that to you, you'd be really bored. But most of all, Scripps for UC SHIP funds for funding and Project Kaisei were a huge help in all of this. And then, of course, all of our friends and family and scientists and advisors and everyone who supported us. And as a group, this is a clean beach, we're happy to answer any questions.
Sure, the question was how far did we drag the nets and how fast did they fill, so getting a feel for how much was out there. Almost all the plastic that we got that was microscopic was collected in the surface tows, a net called a Manta net, which is, we saw pictures of it, has little wings on the side, and it has a big mouth that opens like a manta ray. And we did the standard way of towing, which is you tow it for 15 minutes at 1 knot, which ends up being about a 1/4 mile. And so it's about a swimming pool size amount of water. And in that water, we would find, I'm finding like 500 or so pieces of plastic. It is not as, there are not as many pieces of plastic as plankton, as individuals of plankton. So I know sometimes there's ratios that go around. So that's in very preliminarily, that doesn't seem to be what we're not finding more plastic than plankton numerically, but it just looks like a snow globe. When you take all the stuff that collected in the back of the net and you put it in a little jar, it really just has all these little pieces swirling around. So does that help give you a visualization? The question was, is there a distribution of the sizes? You know, we showed some of the small ones and we also saw some big ones. Check back with us in 6 months to a year. And we do think that the size is related to how long it's been in the ocean, but we don't have a really good quantitative way of looking at that yet. We're working on it. The question is, what can we as citizens do to stop plastic from going into the ocean? We think that the only number that's out there is it's thought that about 80% of the debris comes from land-based sources. So that's improper disposal of waste. That's littering and things blowing in on the beach and trash that gets thrown into the canyons that washes out when it rains like it did on Monday. So I think there is a lot of work to be done by encouraging people to not throw trash around, because that's how it gets into the ocean. So I don't think that a significant amount of debris that is disposed of properly ends up in the middle of the Pacific. Although I do want to mention that it was legal to dump plastic off ships into the ocean until 1993, I believe. Correct me if I'm wrong. 88? 89? I'm going to center in on that eventually. But if you really care, I can get back to you. But so that's at least what I think. Do you want to add anything?
I will say one thing, and one thing I heard you say was that we think a lot of this comes from Asian countries, and sometimes it makes me sad to hear things like that, because I think this is a hard issue to point fingers at anyone. It's all of our fault. We all are guilty of littering at one time. It was legal, like Miriam said, until '89. So it's just a matter of what we can do, right? And I think education is huge. So if all of you tell 2 people, that makes a big difference.
is the amount of plastic out in our study area similar to what you might find in other places? And we looked at this in a brief manner by spending 4 days in the California Current close to Point Conception. We did the same tests there. We did the same sampling, same nets, same everything. And then we have that to compare to what we found in the gyre. And also, I believe we have all en route data every 4 to 5 hours. Is it 4 hours? We stopped to do a Manta tow.
6, actually.
6
Sorry,
hours.
6, yeah.
Okay. So were all those little flags in your picture Manta tows? No. Okay.
We did
But
132.
well, there was 132, little spots that we stopped to put the net over the board. So every 6 hours, the ship would slow down. We'd put the net over. We'd sample the water, pull it in, and the ship would go full speed again. So we should have a continuum from the California Current, where we spent 4 days, all the way out to the center of the gyre, which is thought to be the concentration zone. We went to where we thought there would be the most. It's a convergence zone. And so the floating materials should end up there. So we don't have any preliminary results you want to share?
No.
No. In theory, that we should see less plastic in the California Current and more plastic in the convergence zone, and perhaps an increase as we get closer.
I can actually I do want to add just the visual debris, the little pieces that are still visible, we started seeing at 128 degrees west, which is a couple hundred miles west of San Diego, but well short of the gyre. So we did see it begin before the gyre, although the highest densities that we found were the furthest west.
I think I understand your question. So I think you're trying to say, well, if the organism eats, oh, I do get what you're saying. If the organism eats the plastic and they can't digest it and it's sitting in their system, how do they get these pollutants? So when you think digestion, usually we think breakdown, right? So you have to remember that these pollutants are adsorbing, which means they're sticking to their surface. So even if the plastic breaks apart into little pieces in your body and goes out, that won't make the difference. The difference is the fact that they're on the surface, and the minute it gets into your body, it's so attracted to your fat and your lipids in your body, it's just going to go onto there. So it's not. Does that make sense? Did I answer the question?
It's not inside the plastic, it's on the outside of the plastic.
Yeah, it's more like what the chemical likes better. It prefers your fat over the plastic, unfortunately.
The question was, what is with the size of Texas, and maybe there's plastic in other places? Is that an accurate okay. Excellent. So no, we make no claim that the only plastic in the world is the plastic that we found. Which I wish we could make that claim, because that would mean there was less stuff floating around the ocean, but absolutely not. We can't assess how big it is from the existing published scientific data, because there's just not enough. It's really hard to figure out how big things are in the North Pacific. It's a huge area. The North Pacific Gyre is 20 million square kilometers. It's like 5 United States. So there isn't enough data to say exactly how big of an area is covered by plastic. And then what do you mean by the size of Texas, right? Does it mean that I found 300 pieces of my Manito or only one?
No, I don't mean
yeah.
I mean this myth.
Well, it's not really necessarily a myth, yeah. We cannot confirm nor deny based on existing data. Do you want to add? Yeah.
We can say that our cruise path was 1,700 miles.
3,000. We found it for 1,700 miles.
All right, we found plastic for 1,700 miles. I Google Earthed Texas, and it's 1,100 miles across, so it is bigger than Texas, at least when we were there.
Bigger than Texas in one dimension, yeah. But these are from our data, we will not be able to say how big the total plastic in the North Pacific Gyre is. We'll only be able to say how much we found where we went.
He's wondering about the legislation. So what can we do in terms of policy, in terms of pollutants on the plastic, pollution in the ocean, how is the plastic getting out there? So actually I sat in on a meeting in Sacramento a month ago, and one of the big things that people are starting to do are the bag bans. And unfortunately, it's by city. So it really depends on the city. So if you want to see something like a bag ban, you can write your local congressman for things like that. In terms of there's a new movement called green chemistry, which they are trying to figure out, well, how can we better make plastics? And you see these biodegradable plastics all the time made out of cornstarch. I've eaten that styrofoam. It's completely fine. somebody dared me and I did. So things are moving. They're moving slowly, but the more we get this stuff out there, the more it'll move. And so I think you can always write to your local people. This is kind of a local issue. The thing with it out in the middle of the ocean, what's so hard is it's past anyone's water, right? So in terms of cleaning up that, nobody wants to take responsibility, but in our own towns, we can take responsibility. One more thing I want to say, and then I'll stop, is for recycling, you'll notice if you look, depending on where you live, like in Davis, it's a really green city, yet we only recycle 1s and 2s, and you can physically recycle all plastics. So that's a big thing, is try to get everything to be able to be recycled. I know San Francisco's on it, so we can try to be on there too. I think San Diego might be 1 and 2s as well, so.